Okay, so we were we have presented all of these examples previously in last two lectures of the course. So we have said that Z is a group under addition and it has identity 0 and inverse minus k, and it is abelian. Q plus is a group under multiplication. Zn is a group under addition modulo n. R star and C star are groups under multiplication. GL2F under matrix multiplication is a group. It's not an abelian group. U of n is a multiplication mod n group. It's a group under multiplication mod n. Rn, which has n tuples, is a group under component wise addition. SL2F is the group under matrix multiplication. Dn was, which was the first example, is a group under a matrix, under functions composition. Now, the goal of the abstract algebra is to discover truths about algebraic systems, that is, sets with one or more binary operations that are or that are independent of the specific nature of the operations. All one knows or needs to know is that these operations, whatever they may be, have certain properties. We then seek to deduce consequences of these properties. This is why this branch of mathematics is called abstract algebra. It must be remembered, however, that when a specific group is being discussed, a specific operation must be given. Okay? So now we are talking about elementary properties of groups. Okay? So this means now that we have seen many diverse examples of groups, so we wish to deduce some properties that they share. The definition itself raises some fundamental questions of the group. Every group has an identity. Could a group have more than one identity? Every group has an inverse. Could an element have more than one inverse? And the examples suggest not, but the examples can only suggest. You cannot prove something from an example. So one cannot prove that every group has a unique identity by looking at examples, because each example inherently has properties that may not be shared by all groups. We are forced to restrict ourselves to the properties that all groups have. That is, we must view groups as abstract entities rather than argue by example. So, we will present some theorems to illustrate the abstract approach. So, theorem 1.2.1, theorems are the best thing in this course. Theorem 2.1 says uniqueness of the identity. Now, what is the statement? Statement is, in a group G, there is only one identity element. Is that so? Let's try to prove it. Proof. So we suppose if there is only one, we suppose there are two. Suppose both E and E prime are identities in G. Then what we know? Number one, we know that AE is going to be A for all A in G. And if we have E prime, that means we also have two, which is E prime into A is going to be A. And this is also for all A in G, right? Now the choices of A is equals to E prime in part one, the choices of A is equals to E prime in part one, we're talking about this, and A is equals to E in part two yield that E prime into E is E prime, because from part one we have A into AE is A, so E prime into E is E prime, and from part two we have E prime into E is E. Thus, E and E prime are both equal to E prime E, and so are equal to each other. Because this can't be true for any other element rather than an identity itself. This is the proof. Okay, perfect. Now, because of this theorem, we may unambiguously speak of the identity of a group and denote it by E. By the way, we denote the identity by E because the German word for identity is in heat. I can write that like the German word for entity is in heat. So we denote the an identity of group by E. Okay, perfect. Now we can say something more. In theorem 2.2, That is about cancellation. Statement is, in a group G, the right and left cancellation laws hold. That is what? That is BA is equals to CA implies that B should be C and AB is equals to AC implies that B should be C. Proof? And these are very important laws and they give you something unique. So suppose what can we do to prove it? It's simple. Let's say BA is CA. Just need to show if you are saying BA is CA, then we just need to let A prime be an inverse of A, then multiplying on the right by A prime, then multiplying on the right by A prime yields BA A prime is equals to CA A prime. Now associativity property gives us yields that we can write B A into A prime, C A into A prime, and then we can say BE is CE, and therefore B is C. Similarly, to prove it, what can we do that similarly one can prove that AB is equals to SC implies B is equals to C, that we multiply A prime from the left with AB A prime with SC. This gives by associativity A prime into A, B, and A prime into A, C, and this is E, B, E, C, and this gives B is C. Okay, this is the proof. Now, the consequence of this cancellation property is a fact that in a Cayley table of a group, each group element occurs exactly once in each row and column. And another consequence of this cancellation property is the uniqueness of inverses. And that is our third theorem. So our third theorem says uniqueness of inverses. The statement says for each element A in a group G, there is a unique element B in G such that AB is BA is E. Now we can prove this by assuming that there are two inverses for single element. Suppose B and C are both inverses of A, then AB will give you E and AC will also give you E. So that AB is AC, AC. Now cancelling the A on both sides gives what? Gives that B and C are equal. Okay, this is the perfect consequence, right? Perfect. So identities are unique, inverses are unique, and there is cancellation property in the group. Very nice. One last thing. One last thing is we call it socks shoe property. It is a theorem it's 2.4. Name is socks shoe property, which says that for group G or group elements A and B, AB whole inverse is equal to B inverse A inverse. Okay, perfect. And we can prove that by saying that since AB product AB inverse is E by principle, right? And AB product B inverse A inverse is what? A B inverse B into B inverse A inverse, and this is A, E, A inverse, and this is A, A inverse, and this is E. So we have by 2.3. So we have by theorem 2.3 that unique inverses are unique, that AB inverse is going to be B inverse A inverse, and that's it. So we will talk today, we will only talk about these 4 theorems, and then we end our second chapter, groups. So we define the definition, we have defined the examples, a lot of them, around 19, and then we have presented 4 theorems, and that's it. Try to learn them properly, understand them properly, and if you have any questions, please do tell me in the comments and then I'll explain. Thank you.